Good day, everyone. I am Carla Garrido, and alongside me are Mr. Juan Carlos Castro and Mr. Adam F. Valmeo. Today, we will be presenting our study entitled Vapor Liquid Equilibrium Modeling of R125 and Ammonia Binary Mixture. This study focuses on developing a reliable thermodynamic model for the R125 ammonia system, which is of significant industrial importance in low GWP refrigerant blends. The system exhibits strong non-ideal interactions and double azeotropy, making accurate prediction of phase behavior challenging. By addressing these complexities, the study aims to describe thermodynamic behavior of the R125 ammonia system and its implications for industrial refrigeration applications. Starting off with the research problem. The R125 and ammonia mixture present significant challenges in thermodynamic modeling. Firstly, obtaining reliable experimental VLE data is difficult due to the high volatility and corrosiveness of ammonia and the handling restrictions of R125, which limits available measurements. Secondly, the mixture exhibits strong non-ideal behavior and double azeotropy caused by molecular polarity difference and hydrogen bonding, making phase equilibrium predictions complex. As a result, the lack of accurate experimental data combined with these complex molecular interactions hinders the development of reliable thermodynamic models, which are essential for the safe and efficient design of refrigeration and absorption system. Moving on to the research gap. Existing thermodynamic models have limitations when applied to systems like R125 and ammonia. Conventional activity coefficient models such as Wilson, NRTL, and Uniquark are effective under low pressure, mildly non-ideal conditions, but cannot accurately capture the strong non-idealities in the system. In addition, the Peng-Robinson equation of state is widely used in industry but tends to underrepresent the liquid phase non-idealities in polar nonpolar mixture. On the other hand, the Wong-Sandler mixture or mixing rule improves accuracy by integrating excess Gibbs energy models with PREOS. Yet its application to the R125 and ammonia system is limited, and validated parameter sets are scarce. Therefore, a robust computational framework combining PREOS and Wong-Sandler mixing rule and unified activity coefficient model is needed to accurately predict the non-ideal vapor-liquid equilibria of this binary mixture. For the methodology of this study, several thermodynamic models were applied to describe the R125 and ammonia system. These models are first, Peng-Robinson equation of state, second, Wong-Sandler mixing rule, third, the non-random two-liquid model, and lastly, the Dortmund modified Uniquark model. Starting off with the Peng-Robinson equation of state. This was used to model the PVT behavior of both vapor and liquid phases. Its advantage lies in its ability to handle a wide range of temperatures and pressures, providing a robust baseline for general phase behavior. However, it is limited in representing strong liquid phase non-idealities, particularly in polar nonpolar mixtures like R125 and ammonia. To address this limitation, the Wong-Sandler mixing rule was employed. By integrating excess Gibbs energy into the EOS, this approach allowed the model to capture non-ideal liquid interactions, improving accuracy in regions of high deviation such as azeotropes. In addition, the NRTL model supplied reliable binary interaction parameters which are essential for representing molecular level interactions in the liquid phase. Its strength lies in its thermodynamic consistency, though the parameters are fixed and cannot adapt dynamically to conditions outside the calibrated range. Finally, the Dortmund modified Uniquark models provide structural parameters, including molecular volume and surface area, denoted as R and Q, which enhance the calculation of Gibbs energy and ensured compatibility with NRTL contribution in the Wong-Sandler mixing rule. This model is particularly effective in capturing size and interaction effects, but it requires validation against reliable data sources.
Welcome to the results and discussion section. We will begin by evaluating the performance of our model using absolute average deviation, followed by examining the predictive VLE diagrams, including TXY and PXY plots. Finally, we will present the key output of our work, the regress diagrams, comparing our fitted model directly against the experimental data to validate our chosen thermodynamic approach. This figure illustrates the absolute pressure deviation across the liquid composition range resulting from our data reduction process. The plot shows the difference between the experimental pressure and our calculated pressure at each point. Notice the maximum deviation peaking around x sub 2 is equal to zero point 0.2 at approximately 32 pounds per square inch absolute. The overall shape of this curve confirms that the chosen interaction parameters successfully minimize the average deviation across the entire composition spectrum, giving us the statistically best fit model. Moving to our first predictive result, this TXY diagram was generated at a fixed pressure of 5 bar using unifact derived parameters for the activity coefficient. The solid line represents the bubble point temperature, and the dashed line is the dew point. The curves are clearly separated, indicating significant non-ideality in the liquid phase, which is expected for this polar mixture. This provides a necessary baseline before considering the experimental isothermal data. Here is the purely predictive PXY diagram calculated at 300 Kelvin, assuming a binary interaction parameter of K sub 1 2 is equal to 0. While the general trend and shape of the VLE envelope are captured, we can see the predictive curves lie slightly lower than what is expected, illustrating the limitations of using a zero interaction parameter. This result serves to emphasize why regression against experimental data is essential to accurately model complex mixtures. The XY diagram is crucial for designing separation equipment. This plot compares our regress model calculation against the experimental vapor compositions. The close proximity of the calculated curve to the experimental points confirms that our regress model, utilizing the fitted K sub 1 2 parameter, successfully captured the actual phase equilibrium behavior and relative volatility of the mixture. This final figure presents the most impactful result. The regressed VLE model compared directly to the raw experimental data. The calculated bubble and dew point curves pass remarkably well through the experimental points. The regression process successfully determined a K sub 1-2 value of 0.0572, which allowed the Penn-Robinson with Wong-Sandler mixing rules equation of state to accurately and reliably represent the entire vapor-liquid equilibrium range for the system.
So to conclude our findings, I'm going to walk through the four main conclusions we drew from this thermodynamic study of ammonia and R125 system. So first, we've definitely shown that this mixture exhibits extreme non-ideal behavior, while a simple ideal model like Raoult's law can predict which component is more volatile. It's the excess properties that reveal the true story of the molecular interactions. So we found out two conflicting factors and behaviors. On one hand, a positive excess gives energy, gives us that the components have a reduced tendency to mix compared to an ideal solution. But on the other hand, a negative excess enthalpy and volume show that the mixing is exothermic and the molecules pack together tightly, which suggests a strong attractive forces like hydrogen bonding. This combination of positive excess gives energy and negative excess enthalpy is the key takeaway. It points to a very complex system where strong, favorable associations are being counteracted with large differences in molecular size and shape. Our second major finding is a critical phase symmetry. Since the vapor phase is simple, it behaves nearly as an ideal gas, with fugacity coefficients remaining close to 1. But in contrary, the liquid phase is extremely non-ideal. The fugacity coefficients here show deviations that are orders of magnitude higher. This is a crucial insight since it confirms that the bulk of the non-ideal behavior or the complex physics that we need to worry about is confined almost entirely to the liquid phase. Third is this extreme non-ideality isn't just theoretical. It has a clear and very challenging physical manifestation, which is the double azeotropy. This is the direct evidence of those competing molecular forces we saw in the excess properties. In the ammonia-rich region, we get a positive deviation azeotrope, or a minimum pressure point. This happens because the associative ammonia molecules prefer to bond with themselves, effectively repelling the R125 and increasing the system's volatility. But in the R125 region, the behavior flips. We get a negative deviation azeotrope, or a maximum pressure point. This is likely caused by the formation of a specific favorable complexes between ammonia and R125, which reduces the system's volatility. So finally, let's talk about the model itself. To capture this double azeotropy, we had to use the Peng-Robinson equation of state with Wong-Sandler mixing rules. While our data reduction process resulted in an excellent statistical fit with an AADP of 0.77 PSIA and an AADY of 0.0076, we have to be clear that this success is primarily achieved by curve fitting. The core limitation is this: the model success hinges on a single global binary interaction parameter, or K sub 1, 2, which we optimized to 0.0572. A single parameter is structurally incapable of physically representing two fundamentally conflicting behaviors: the positive deviation and the negative deviation of K12. So this value is therefore a compromised value that minimizes the overall error. It does not hold reliable physical meaning across all compositions. So what does this all mean? It means that the PRWS model is an excellent correlative tool for this system, but it is not a truly predictive tool. For future work on the systems characterized by self-association, like ammonia, a more advanced model is required. We recommend to we recommend using a cubic plus association, or CPA, equation of state. A CPA model is specifically designed to explicitly account for the hydrogen bonding term, which allowed us to move forward or beyond the empirical curve fitting and towards a model that is both accurate and physically meaningful. So this is the end of our presentation. I hope you have some key takeaways from our study, and I hope that you learned something. Thank you.